Hi, this video will cover section 2.5, zeros of polynomial functions. And we have several objectives, so I'm going to try to mention them quickly. One of those will be the fundamental theorem of algebra to determine the number of zeros of polynomial functions. This one has something to do with factoring. Then the second objective, find rational zeros of polynomial functions. I want to remind you that rational numbers are those numbers that could be written as the ratio of two integers. So they will look like either integers with a denominator of one or like a fraction, and they could be positive or negative. The next will be to find conjugate pairs of complex zeros. We did a little bit of this on section 2.4. Then find zeros of polynomials by factoring. And we have used the cart rule of signs in the upper and lower bound rules to find zeros of polynomials. This was very popular when calculators were not available. And find zeros of polynomials in real life applications. So let's get started. So we have the first theorem mentioned here, the fundamental theorem of algebra. And this theorem is defined in the complex number system. So every nth degree, nth is going to be our degree, and here we go. For every nth degree polynomial function has precisely n zeros. And so in the previous sections, we had said that depending on the degree of the polynomial, it could have at most those many zeros, or it could have less. Now we are saying that was in the real number system, but for the complex number system, it's going to have exactly n zeros, the same as the degree, and that is because we will be counting the imaginary zeros as well as repetitions. So this important result is derived from the fundamental theorem of algebra, first proved by the German mathematician Carl Friedrich Gauss, the same guy who we're going to study a little bit more in chapter 8. He did a lot with matrices. And here we have the formal definition. So it says if f of x is a polynomial of degree n, and n is greater than 0, so we're not including the constant functions of degree 0, then f has at least one 0 in the complex number system. So if we go to the next slide, we could see how the number of zeros will also translate into the number of factors. So with that, we could go to the linear factorization theorem. And so here, if we use each factor to be of degree 1, that's why we call it linear factorization theorem, we could factorize a polynomial in this form. So if the polynomial is of degree n, and that's why we have here the a sub n as the leading coefficient, so where n is greater than 0, so we will start at n equals 1. And of course, a linear function is already factored in linear form. But if we had a quadratic function, we could also factor it that way. And here, for the constants that you see being mentioned here, c sub n, c sub 2, c sub 1, and all the ones that are in between within the factors, for those constants, we're not just saying that they are real numbers. We're actually saying that they're going to be complex numbers. So again, some of these factors might have imaginary numbers. It could be, I don't know, something like x plus for I. That could be a factor. And it is in linear form because the exponent of x is a 1. And here we're just saying that the constants will be complex numbers. So it could be a real number. Remember, they're divided into two, the real numbers and also the imaginary numbers. Okay, and I was supposed to make an R right here. Okay, so that's what we're going to be doing. We're going to find all the factors because that way we will be finding all the zeros or solutions or roots, whatever you want to call them. Now remember that only the zeros that are real numbers will appear as x-intercepts. A zero that would come from here, which would actually be something like x is equal to negative 4i. So that zero will not be visible as an x-intercept when you graph your polynomial. Okay, so let's start here with example 1. So the first example 1, part A, we have a linear polynomial or linear function. You can see that highest exponent is a 1. And so because n is equal to 1, the polynomial has exactly 1 0. And this one happens to be, if we make this f of x equals 0, and then we solve for x, we will see that it will equal to x equals to positive 2. So that 0 is 2 at 2. Since it is a real number, the x-intercept will be the point 2, 0. Next, part B, we have a polynomial of second degree. And you can see that because of the exponent that we have there. So if we want to find the zeros, for example, of this polynomial, well, first of all, it will have exactly 2 zeros. Okay, so I'm going to try to factor it. F of x is equal to the product of two binomials. And these two binomials will be x minus 3, x minus 3. So this polynomial can actually be factored this way, x minus 3 to the second power. And so because of that 2 on the factors, we're going to say that it does have multiplicity of 2. However, if we look at each factor individually, 2 zeros will come from it. So here we will have x equals to 3 and x is equal to 3. Remember, we equal it to 0, each factor. I'll just do an example here. X minus 3 equals 0, and then we solve for x, so that's how I get x equals 3. Now, we had 2 of those factors, or you can look at it here at the exponent. It's a 2, so it does have even multiplicity. And remember, those are the zeros that will touch the x-axis, and then it will bounce back or turn around. All right, so the next polynomial, we have something of third degree. And so this polynomial is going to have exactly, since n equals 3, is going to have 3 zeros. And let's see if we can find them. So I'm going to factor here. Here, what they both have in common is x. So I factor out x. And then x cubed divided by x is x squared. Then plus 4x divided by x is plus 4. So now from here, we equal the function to 0 because we're after the zeros. And now by the zero factor property, we make each factor equal to 0. to solve for x. So the first one here, x equals 0, we already have one. So out of these three zeros, we have that x equals 0 is one of those. And that means that you will have a point at 0, 0. Okay, what else? So if we take the other factor, x squared plus 4, and equal it to 0, and then we try to solve for x, you could see that x squared is equal to negative 4. And here in the real number system, we have no solution. However, we already covered complex numbers, so that is what we're going to find. So if we take the square root on each side of the equation, you could see that the x squared gets canceled. Then the right side will be the square root of the product of negative 1 times 4. And from here, we could say that x is equal to the square root of negative 1 times the square root of 4. Now, the square root of negative 1 by definition is I, and the square root of 4 is 2. But in reality, we also have negative 2. In this case, we're going to use both the positive and the negative square root of 4. We could also say here, I mean, if we wanted to write them one at a time, sometimes you might have to separate them with a comma. So I'm not sure if WebAssign has that ability to, that button for a plus minus. So keep in mind that you might have to write one at a time. So positive 2i and negative 2i. One thing that these two numbers have in common is that they are complex conjugates of each other. So one of them is 0 plus 2i, and the other one is 0 minus 2i. So it is no coincidence when you have a 0 that is complex, not just complex, but imaginary, you will have the complex conjugate there as well. So you have 2i minus 2i. So if you count them here, we have 1, 2, and 3. So we have exactly 3 zeros. 2 are imaginary, 1 is real. And if we look at example B again, we have exactly 2 zeros. They just happen to be the same number. They are repeating. Okay, now the next theorem the rational zero test. So for this one, is the one that we're going to use to find zeros that are rational numbers. So this is reserved to those zeros that will be real numbers, but remember they could be, the denominator could be 1. That is very common. So for the numerator of those zeros, we are going to look at the constant term, a sub 0. And so the letter P represents the factors of that constant term. So if that constant term was a 1, we wouldn't have an issue because it would just be 1, the only factor. If that constant term is a 2, the factors will be 1 and 2. But also they could be negative 1 and negative 2. Now, if that constant term was like a 6, then we will have several factors, 1, 2, 3, and 6. So that's how we're going to work the problem out. And the letter Q is representing the factors of the leading coefficient. And remember, the leading coefficient is here. The coefficient of the leading term, meaning the x with the highest exponent. So we're going to get the factors of that leading coefficient. Most of the time that leading coefficient is a 1, so it makes things a lot easier. But yeah, sometimes it might not be, so we might have several possibilities. Now I want to clarify that with this test, the rational zero test, we are finding possible zeros. It doesn't mean that all the numbers that we find will be the zeros. And so once we find all the possibilities, we'll be testing them to see if they are in fact a zero or a solution of the polynomial. How are we going to test them? Well, we're going to use some of the skills that we learned last section, such as synthetic division. Okay, so let's get started here with example 3. And for example 3, we're going to take first the constant term, which happens to be a -6. So we're going to get the factors of -6. And so those will be 1, 2, 3, and 6. But we are also going to consider the negative ones. So plus minus 1, plus minus 2, plus minus 3, and plus minus 6. So now we got to look at the leading coefficient. And you could see that it is a 1. We don't have a number, so there's an implied 1. So that is a very good sign. So that will be the denominator. In fact, we not only have 1, we have positive 1 and negative 1. So what's going to happen out of all the possible numbers that we could have here, which will be the possible rational zeros, and remember these are just possibilities, we're going to test them, and so that will be positive 1 and negative 1, positive 2, or we could, I don't need to put the positive sign, positive 2 and negative 2, then positive 3, negative 3, positive 6, and negative 6. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different possibilities. And this is a good amount because we were just dividing by 1. Sometimes the leading coefficient, if it's a bigger number, we will have more factors here in the denominator, and therefore we'll have more combinations. So, and we'll have some fractions. Okay, so what we're going to do next, and here you are welcome to graph your polynomial and see where it's touching the x-axis. And that way you could start testing zeros that will be more likely to be zeros, or test possible numbers that will be more likely to be zeros. I call that making an educated guess. But here, the PowerPoint is already giving us a hint. So they want us to determine if x equals -1 from this list and x equals 2 are the only 2 rational zeros. So we are going to test a -1 and a positive 2. So we're going to use synthetic division, like I mentioned. So first we try -1, and we need the coefficients of the polynomial. Remember, we have to make sure that we're not missing any terms, like we have to have consecutive exponents, like to the exponent 4, 3, 2, 1, and the constant term is known to have an exponent of 0. So we have to make sure they're in order, descending order from larger exponent to smallest exponent, and also that we're not missing any variables in between. Like if we didn't have an x squared, for example, we will have to use a placeholder of a 0. Okay, so let's see. The coefficient of x to the 4 is a 1. The coefficient of x cubed is a -1. The coefficient, of x squared is a 1. And the coefficient of x is a -3. Coefficient of 6 is a the constant term, I should say that. It's a -6. Okay, so now let's go ahead and perform the synthetic division. So we drop the first digit, then we multiply -1 times 1, that gives me -1. Combine like terms, so that's -2. We multiply negative times a negative, so that's positive 2. We add vertically or combine like terms, so that's a 3. Then we multiply -1 times 3, that gives me -3. -3 minus 3 is -6. And then we multiply again, -1 times -6, so that gives me a +6. And if I combine like terms, I get 0. So because 0 is the remainder, we could say that the expression, not the expression, x equals -1 is a 0, meaning that for that x value, the y is equal to 0. But that's why we call them that. Since it is a real number, we could actually see it on the graph with an x-intercept at -1, 0. Don't forget that. And since we have this equation as a 0, we know that the factor is going to be x plus 1. That is the factor. Like if you were to take this -1 across the equal sign, it will turn into +1. So that is one of our factors. Okay, now we are going to apply synthetic division again, but we're going to use the same, not the original coefficients from here, but we're going to use the new ones. And now we're going to test 2 to verify that that is another 0 of the polynomial. I can tell you, yes, it is going to be, but we still need to check. So we drop the first digit. 2 times 1 is a 2. -2 plus 2 is 0. 2 times 0 is 0. 3 plus 0 is 3. And 2 times 3 is 6. -6 plus 6, 0. So again, we get a remainder of 0. So what does that mean? That the value x equals 2, we call it a 0 of the equation, or a solution of the polynomial. So we already know that it's a real number, so the x-intercept is going to be occurring at 2, 0. And also, we know that the factor that will come from this solution is going to be x minus 2, and then in parentheses, because we're talking about factors. So we could see those two here. We have x plus 1. It's right here. And then we have x minus 2. That's the one that we got from here. And then we have another factor, and that is the one that came from here, from this new coefficients. So we started with a polynomial of degree 4. So this is x to the 4th power. This is x to the 3rd power. Those were the new coefficients that we got after dividing once. And then after the second time, that will be 1 degree less. So this is x squared. The 0 represents x, and then 3 represents the constant term. So that's why this is 1x squared plus 3. And that is the third factor that you can see here, x squared plus 3. Now, if we were asked to find the zeros, remember this is degree 4, so we should have 4 zeros. So if we take that third factor, the x squared plus 3, equal it to 0, and then try to solve for x, we will get x squared is equal to -3. So by taking the square root, we wouldn't get a real solution, but we will get the square root of -3, which could be factored as -1 times 3. And what that means is that x is equal to the product of the two square roots, the square root of -1 times the square root of 3. And so at this point, we could use the square root of -1, which will be I by definition. And then the square root of 3, we leave it inside the radical sign because it does not have an exact answer. Of course, if whatever sign is asking you to approximate, type that in your calculator and get a decimal, a solution in decimals. Make sure you round accordingly. And here we could also use the plus minus. Remember that conjugate imaginary zeros, they come in pairs, conjugate pairs. So right here we're saying x equals positive I square root of 3, or we could say square root of 3 times I. And the fourth zero will be x equals negative I square root of 3. Okay, so right here, this takes me to my next theorem that says that complex zeros are conjugates. So if we have a plus bi, we have a minus bi. The ones that we just found were 0 plus square root of 3i, and the other one was 0 minus the square root of 3i. Like I said, they occur in pairs, and they are conjugate pairs. So if you get a 0 and they ask you to find the rest, you could always assume right away that you will have the complex conjugate as well as the zero of the function. So let's see here. For instance, that applies to the function x squared plus 1. And that will be because if we make this, well, let's read the statement before. It says, be sure to see that this result is true only when the polynomial function has real coefficients. So here we have real coefficients. The coefficient of x squared is a real number, a 1. And the next one, which is a constant term, is also a real number. So here, the coefficient of this function is not a real number, so the theorem does not apply to a function like that. But for this one here, we could find the zeros, x squared plus 1, so we'll have -1 is equal to x squared. We take the square root on both sides, and then we will get x is equal to plus minus I, meaning that x will be 0 plus I, and x could also be 0 minus I. So those two are complex conjugates. Okay, so next problem. This is one of the most difficult ones from this section probably. We're asked to find a fourth degree polynomial function with real coefficients. So that means that we can apply the previous theorem, and they're giving us some of the zeros. So we have that -1 and -1, and they're listing it twice. So then if we have x equals 0, here, actually I'm gonna make a table. So if we have x equals -1, we have the factor x plus 1. And we have it twice. So we have x plus 1 again. And if we have this 0 here, which is imaginary, it's positive 3i. And so the factor that comes from it, it will be x minus 3i. Just like that. And by the complex conjugate fact about zeros, we also have -3i. So then the factor is going to be x plus 3i. And this one here is negative. So what we're going to do is we are going to multiply this 2 first, and then we will multiply the two complex conjugates. So let's do that. So we have x plus 1 times x plus 1, or this is the same as x plus 1 to the second power. So the product that we will get from here is going to be x squared plus x plus x plus 1. So after combining like terms, we will get x squared plus 2x plus 1. So we're going to save this polynomial. And now let's work with the other two. So x minus 3i times x plus 3i. And this will be x squared plus 3xi. That's what I will get from here and here. And then minus 3xi, and that's the product I will get from here and here. And then at the end, I'm going to have to multiply negative 3i times positive 3i, so it's going to be negative 9i squared. So you could see that two terms in the middle will cancel out because they're opposites. And now we just have x squared plus, not plus, but minus 9. And then I squared is replaced with a negative 1. By definition, that's what it is. So this is x squared plus 9. So let's say that WebAssign wants the 4th degree polynomial. If they are okay with you writing your answer and leaving it in factor form, then it will be completely acceptable to write it this way. Or even this way. That will be perfectly fine. But they might want you to actually carry out the multiplication. So we already know what the product of this one is. So it will be x squared plus 2x plus 1, and that is times x squared plus 9. So if we work this problem out, let's just do it down here. So it will be, first we could take this x squared and we'll distribute it to the x squared plus 9. Then we could take the plus 2x and distribute that to the x squared plus 9. And then we could take the positive 1 and distribute it to x squared plus 9. So then here, I'm going to go ahead and start multiplying. So here we'll get x to the 4th, and then plus 9x squared. And then I will get plus 2x cubed, and then plus 18x, and then plus x squared plus 9. And let's go ahead and combine like terms. So x to the 4th, we only have one x to the 3rd power, or 2 I should say. And then we get 9x squared and 1x squared. So that's a total of 10x squared. Then we have plus 18x and then plus 9. And so, yeah, that will be the solution of the polynomial. Now, that is only because they're telling us here for simplicity, we'll let a equals 1. What is a? Well, a is actually the leading coefficient in this case. So it will still be here outside multiplying. In other cases, you might have to find what a is. And the way you will do that is by, you will be given a point. And with that point, once you have your answer, whether it's in expanded form or in factor form. What is this? Oops. So once you have your answer in factor form, and if you have to find a, they might give you an x value. Let's say when x equals 2, y equals 3. Or they might give you something like f of 2 is equal to 3. So then in that case, what you will have to do, and you might have some of this on your homework, you might have to replace the y value, or this whole thing, f of x, with the number 3. And then you will have to replace every x with the number 2. So here and here. Or if you're doing it with the factor form, you replace f of x with the number 3, the y value, the output. And then you replace every x with the number 2, whatever point or value they give you. For this example, for simplicity, it says here a equals 1. So we don't have to worry about it. But you might have a problem like that on your homework. So you will do that, replace that, and then that's how you will find the value for a. And it's kind of easier in factor form. So to factor a polynomial, the linear factorization theorem shows that you can write any nth degree polynomial as the product of n linear factors. So that's why in here, again, we have the constant a sub n. And here the reason we have n factors is because the last one has that constant with the subscript of n. So we start with the first constant, second constant, third. We don't know how many are in between, but we know the last one will be the nth constant. Therefore, n linear factors. However, this result includes the possibility that some of the values of the constants are complex numbers in the form of the real and imaginary part. Or they might just be pure imaginary. And remember that if we have one of those, we do have their conjugate as well. Okay, so the following theorem says that even if you do not want to get involved with complex factors, you can still write f of x as the product of linear and or quadratic factors. So every polynomial of degree n greater than 0 with real coefficients can be written as the product of linear, and here we're going to include quadratic factors, just if you don't want to deal with the complex factors, where the quadratic factors have no real zeros. Instead of that, those quadratic factors will have complex imaginary zeros, or we could just say complex zeros. So a very good example of that, we already solved this equation, and it was something like the square root, well, let me do it again. We have 0 is equal to x squared plus 1. So if we move the plus 1 to the left, it's a -1. And then we took the square root. We said by definition, the square root of -1 is going to be I. But it's in reality, we'll consider both positive and negative I. So that tells me that my two zeros are x equals to positive I, and the other one is negative I. Now from there, from each zero, we get a factor. So the first factor there is x minus I, and the other one that comes from the zero will be x plus I. And if we were to multiply those two factors, we will actually get the same, the original polynomial before factoring. Also, there are some quadratics that will not have imaginary zeros, but they will have zeros that will be irrational. So for example, the square root of 2 is an irrational number, or any other number that cannot be turned into a fraction, into a ratio. So we use those to denote the exact answer. So if we were to take this equation, x squared minus 2, we'll equal it to 0 because we're finding the zeros or the solutions. So x squared will equal to 2. And if we take the square root, we will get x is equal to plus minus the square root of 2. So that means x equals positive square root of 2 and x equals negative square root of 2. So again, from this positive square root of 2, these are the zeros. We get the factor that you see here. And then from this other 0, with the negative square root of 2, we get this factor, x plus the square root of 2. So those type of zeros are called irrational. And those also come in not conjugate pairs, but I guess, yes, not complex conjugate pairs, but conjugate pairs. Meaning, if you see here, one has the negative, the other one has the positive square root of 2. So those two are opposites. Okay, so example 7, we're going to find all the zeros for this polynomial of degree 4. So since we were given one of those zeros, and I noticed that it is a complex number, 1 plus 3i, we have the complex conjugate as well, and that will be x equals to 1 minus 3i. Okay, so let's find the factors. From here, we will get the factor is going to be, I'm going to take the positive 1 across, so it's negative 1. Take the 3i across, negative 3i. For the next 0, the factor will be x minus 1 plus 3i. Now let's go ahead and multiply those two. So I want to show you how you could also do a vertical multiplication. And so we could take this positive 3i and multiply it by negative 3i, so we will get negative 9i squared. Then positive 3i times this negative 1, and we will get negative 3i. Then positive 3i times x, and we will get positive 3xi. Now I'm going to take the negative 1 and multiply times 3i. So it's going to be negative times negative is positive 3i. And then negative 1 times negative 1 here. So I'm going to get a plus 1. And then finally negative 1 times x, I'm going to get a negative x. Okay, and finally we have the x here. So x times negative 3i, that will be minus 3xi. X times negative 1 will be negative x. And then finally x times x will be x squared. Okay, now I'm going to add vertically, and I purposely place them below if they were like terms. So we only have 1x squared. These two will cancel out because they're opposites. Same thing here. And then what else do we have? Oh yeah, negative x minus x, negative 2x. Then we have a plus 1 there in blue. And then from here, we're going to get negative 9 times negative 1. Recall that anytime we get an I squared, you replace that with a negative 1. So this is going to equal to x squared minus 2x plus 1 plus 9, which is equal to x squared minus 2x plus 10. And that is the product of these two factors. So what we have done is factor out our polynomial starting with one of the zeros, got a second zero, multiply those two zeros, and we found this polynomial. So that is one of our factors right now. It's just in quadratic form. Quadratic because we have a 2 right here. So we're missing another factor here. In fact, we might be missing more, but let's start with one factor. So to find that factor, we're going to take the original polynomial and divide it by that. Now we cannot use synthetic division, unfortunately. Because the degree of our divisor is a 2. Okay, so the dividend is the original polynomial here. So it's x to the 4th. Okay, so I have our polynomial ready, and we're going to take here x to the 4th divided by x squared, and that's going to give me x squared. So now I'm going to multiply x squared times 10, positive 10x squared, x squared times negative 2x, so negative 2x cubed, x squared times x squared. So I get positive x to the fourth. Now remember we had to subtract, so this goes to negative. This goes to positive. And the positive 10 turns into negative 10. And then we combine like terms, so this cancel. Negative 3x cubed plus 2x cubed, we get negative x cubed. And from positive 6x squared minus 10x squared, we get negative 4x squared. Now we drop the next term, which is plus 2x. And now I'm going to divide the negative x cubed by the x squared. So it's going to be negative x. Then I'm going to multiply. So I will get negative x times x squared is negative x cubed. Negative x times negative 2x is positive 2x squared. And then negative x times 10, negative 10x. So now we need to change our signs because we got to subtract. So this goes to negative and this goes to positive. So cancels. Negative 4x squared minus 2x squared is negative 6x squared. 2x plus 10x is 12x. Then we drop the next term. And then finally we divide here. Negative 6x squared divided by x squared. So that will be negative 6. Then I need to multiply. And then finally I need to subtract. So I'm going to change the signs. And you can see that everything will cancel very nicely. The remainder is 0. So what have we accomplished? So we found that the factor that we needed here is this one. So let's go back to where we started. The question said find all the zeros. We already found 2 of those zeros. The degree of the polynomial is 4. So we need 2 more zeros, and those zeros will come from this polynomial here. So let's see if we could just factor it, and we should be able to. So x squared minus x minus 6 equals 0. So we will factor it as the product of 2 binomials. And because this number is negative, that means that we have a positive and a negative there. And factors of 6, we could have 1 and 6, but we could also have 2 and 3. And because we know 1 is positive, 1 is negative, the one with the biggest absolute value will keep the negative sign, so that will be the 3. And the 2 will be positive. Because 2 minus 3 is equal to negative 1, and that's what we needed for the term in the middle. So our factors will be x plus 2 and x minus 3. So just to finish this up, if we have the factors here, x plus 2 and then x minus 3, that means that the zeros that we will get will be, and I just need to verify quickly. Yes, it will be x equals negative 2, and the other one will be x equals positive 3. So then we have our 4 zeros, 1, 2, 3, 4. And that's it. That was the question. Find all the zeros. So we have all 4 zeros. Okay, so the last thing that we have here, well, I say the last, but it's probably not, is the Descartes rule of sines. And this is going to help us to make some decisions. Remember when we had the rational zero theorem? Let me show you one example. Okay, so the one here with the factors of the constant term, the factors of the leading coefficient. So let me just make up a polynomial and we're going to apply that theorem. So let's say g of x equals 6x to the power 4 minus 2x cubed plus x squared, and then let's skip the x term and we'll just put a constant, 5. So if we apply this theorem, we need to get the factors of the constant. So factors of 5, which will be plus minus 1 and plus minus 5. That's it. But then we're going to divide by the factors of the leading coefficient. And that number 6 has several factors. So it could be plus minus 1, plus minus 2, plus minus 3, and plus minus 6. So what we're going to have is several combinations. We're going to have 1 divided by 1, like we have here, and of course a plus minus. And then we're going to have that same 1 divided by 2, so plus minus 1/2. Then we're also going to have that same 1 divided by 3, so it will be plus minus 1/3. Then we will have that same 1 divided by 6, so plus minus 1/6. And then we have to repeat the process, but with the 5. So we're going to have 5 divided by 1, so of course 5 plus minus 5. And then 5 divided by 2, so plus minus 5/2. Then we will have 5 divided by 3, so plus minus 5/3. And then 5 divided by 6, so plus minus 5/6. And we could check, there's nothing that we could simplify, but WebAssign will always want your simplified answer. After dividing, if some are repeating, don't type them twice on WebAssign or it might count it wrong. So here we have a total of 1, 2, 3, 4, 5, 6, 7, 8 possibilities. But if we consider positive and negative, we have a total of 16 possible rational zeros. So if we didn't have a graphing utility, such a calculator or a computer, it will be hard for us to make wise decisions or educated guesses. So back in the day, without that technology, combining this rational zero theorem with the Descartes rule of sines eliminated a lot of the testing that was necessary. And so let me show you how you could use that. And I'm not saying that that is the only way you can find zeros, but for instance, in your homework, on your exam, you might encounter a question that will specifically require you to use the Descartes rule of signs to find how many, and here we're also talking about possibilities, how many positive real zeros you could have, or how many negative real zeros you could have. So the way we will find this is by counting the variations in sign of the original polynomial, and that will give us an idea of how many positive possible positive real zeros we could have. Now, to find the possible negative real zeros we can have, we find first f of negative x. So remember, we replace x with a -1 for every single x. And then we count the variations in sign of that. And that will tell us how many possible, this is not like a given, how many possible negative real zeros we could have. Okay, so what is a variation in sign? A variation in sign means that for two consecutive coefficients have opposite signs, meaning something like, let's give an example. Let's say that we have 3x to the power 5 minus 2x to the power 4 minus x to the power 3 plus 7 to the power x to the power 2, and then let's say minus 3x. Okay, so our first sign here is positive because we don't have anything, so we know it's positive. Now, if we consider from positive to negative, those two consecutive coefficients, we could see, oh my God, I just opened a program. Okay, we could see that it went from positive to negative, so that is considered one variation in sign. One variation. Okay, now from here, it was negative, and then it's negative still, so no variation there at all. But then we go from negative to positive, so that's another variation right there. So we have a total of +1 +1. And then again, we go from positive to negative, so that's considered another variation. Okay, I'm going to pause this video for a second. So this polynomial here, going from positive to negative or negative to positive, it happened once, twice, and then a third time here, from positive to negative, third time. So we have a total of 3 variations in sign. I don't know why this keeps opening. I'm gonna try to close it. Okay, so what does that mean? It means that we have 3 variations. In sign, and so that for f of x. So what that means is that we could have 3 positive real zeros. So we could have 3 positive real zeros. That's just what it means. It doesn't mean that x equals 3 is our zero. It just means that we could have 3 positive real zeros. All right, so when we use the Descartes rule of signs, a zero of multiplicity k should be counted as K0. So if we have a zero, the same number repeating, like having it twice or more, then that will count for each of these possibilities. So one other thing that I should mention that this theorem doesn't mention right here, since we already counted the variations here. So those 3 variations doesn't mean that you could just have that. If you notice here, the theorem says, or less than that number by an even integer. So what does that mean? To that number of variations, I'm actually gonna take this back. So to this number of variations, we could subtract an even integer. What's the first even integer? Oh, well, 0, and then bigger than 0, that will be a 2. So it could be either 3 or, well, actually, I should put it here, or 3 minus 2 is 1. So that is what this part means, or less. So we subtract an even integer. Now, could we subtract 2 again? No, because then 1 minus 2 will get -1, and we cannot have -1 possibility. So it will just be either 3 or 1 of the positive real zeros. So either 3 or 1. Not x equals 3, x equals 1. It's just like counting them, you could have 3 or 1 that are positive. Now, how could we find the ones for negative zeros? Well, we will have to substitute in every x here a negative x, and then expand the expression and see how many, count the variations in sign. So we're going to do that with this polynomial. So right here, if we have f of x is equal to x cubed minus 3x plus 2. And so you could see how we start here with a positive. So from positive to negative, that's 1. And then from negative to positive, that's another 1. So we have 2 sign variations. So what this means is that we could have either 2 positive real zeros. But remember that part that says subtract an even integer. So if I subtract 2, 2 minus 2 will be 0, meaning like none. So no positive real zeros. That could mean like, oh, well, maybe all your zeros are negative. And think about all those possibilities that I showed you before, like 16 possibilities. Then that could cut your work, your testing, by half, because then you wouldn't have to test any positive real number. Okay, so let's go ahead and find how many for negative x. So f of negative x, we substitute that and to the original, and it will be negative x to the power 3 minus 3, substitute with a negative x, and then we have a plus 2. So if I calculate this, it's going to be negative x to the power 3. Then here, negative times negative gives me a positive 3x, and then I have a plus 2. So now I'm going to count the sign variations of f of negative x. Remember, this was for positive. This is going to be for negative. So we're going to go from negative to positive, that's 1. And then from positive to positive, that's nothing. So we only had one sign variation. What does that mean? That we could only have one possible negative, because we tested negative x, negative real zero. Now, my guess here is that since the degree is a 3, maybe we have 2 positive real zeros and we have 1 negative real zero. Because if n is equal to 3, then we have 3 zeros. Even if they're repeating, we still consider them 2 different ones. So yeah, that could be a good combination. Now, this rule of signs is only for real zeros, no complex or imaginary. Okay, so we're going to do this problem, determine the numbers of positive and negative real zeros. So first we count the sign changes. We go from positive to negative, so that's a +1. Then from negative to positive, that's another +1. And then from positive to negative, so that's another +1. Okay, so we have 3 sign changes or variations. So that means that we have either 3 positive real zeros or 1. And it is a 1 because it's 3 minus 2, 1. Remember, we keep subtracting a 1. If we had, like, let's say 7 sign changes, then it will be, our possibilities will be either 7 or 5 or 3 or 1. Those will be the possible positive real zeros. Okay, now let's find the negative ones. So we're going to find f of negative x. So we will get 3 negative x, to the 3rd power minus 5, and then negative x, and then square, plus 6 negative x, and then minus 4. So let's see here, we will get 3. From here, we will get negative x cubed. And then from here, I'm going to take care of the exponents first, so I'm still leaving the negative 5 there. And then I'm going to have positive x squared. This one, let's go ahead and carry out the multiplication, so negative 6x, and then minus 4. So then finally, we multiply 3 times negative x cubed, so negative 3x cubed minus 5x squared minus 6x minus 4. And as you can see here, we have no sign changes. They're all negative. So what that means, and that is for negative x, no sign variations. It did not change. So that implies that we have no negative real zeros. And so if you look at our possibilities for positive real zeros, maybe it does have 3 because the degree is a 3. Now, of course, it could also have 1 positive real zero, so that will mean that the other 2 might be imaginary, which makes perfect sense. Oh, and we have it here. So that 0, it happens here at positive 1. And either that is repeating 3 times, which I don't think so, no. So yeah, the other 2 must be imaginary. Okay, so other tests for zeros. So
the upper and lower bound rules. So if we let f of x be a polynomial with real coefficients again, and a positive leading coefficient, suppose that f of x is divided by x minus c using synthetic division. So remember how we used to put the little number there? So if that number is greater than 0, meaning positive, and each number in the last row is either positive or 0, then c is the upper bound for the real zeros of f, meaning that you cannot have a number bigger than that. So that's another way to cut the options of the numbers that you will have to test. However, if that number is less than 0, meaning negative, and the numbers in the last row are alternately positive and negative, 0 entries count as positive or negative, like neutral, then that number, C, this one, is the lower bound. If you see alternating signs, positive, negative, positive, negative, in your last row. And for the other one, it was either positive or 0. Positive or 0. Okay, and we have here an example, and it does have the solution actually, so we're just going to go over quickly. So you're designing candle making kits. Each kit contains 5 cubic inches of candle wax. And a mold for making a pyramid-shaped candle. So you want the height of the candle to be 2 inches. And oh, 2 inches less than the length. Okay, so then we want the height to be, let's call the length L. The length of each side. Okay. We want it to be 2 inches less, so minus 2 of the candle square base. Okay, so we have a, let's see, this will be the base, and well, this is if we were looking at it from above, I guess. Yeah, not a very good drawing. Let's assume something like that. Oh yeah, that's a lot better. Okay, so here we're gonna let's just use the same variables here. So we're considering capital B. Well, the question is, what should be the dimensions of your candle? What should the dimensions of your candle mold be? So for the solution, we consider first the formula for to find the volume of a pyramid. And capital B is the area of the base. So it will be this part right here. And we want to call the side X. So if each side is called X, then the area of the base is going to be side square, so X squared. And then the height, just like we said here, and instead of calling it H and L, let's just write it with words. We want the height to be 2 inches less then the length of each side. So it will be the length of each side minus 2. And the height of the pyramid is actually a perpendicular line that comes here. And it's kind of hard to see, but yeah, it will not be slanted. There's also a thing called a slanted height. We don't want that. We want the one that is perpendicular and it intersects the base right at the center. So that is what we are calling x minus 2 right here, the height. So if h is x minus 2 and the area of the base is equal to x squared, we use the formula for the volume of the pyramid, which is 1/3 of the area of the base. That's right here. Actually, I'll just write the formula here. And then times the height. So again, we have the height, here the x minus 2, and the area of the base is x squared. And the 1/3 is part of the formula. So we see here, where is that? Right here. We see that each candle making kit is 20, it contains 25 cubic inches of candle wax. So that's going to be relevant because we want this volume to be equal to 25, what each kit contains of the candle wax. So we substitute 25 V with this 25, and then we have the 1/3 x squared and then x minus 2, like that. Okay, so what we're going to do here for simplicity, we're going to multiply each side by 3 just to clear the fraction. And we do that because we have a 1/3 here. So then we will get 75 is equal to x squared times x minus 2. Okay, now I'm going to go ahead and distribute the x. So here and here. So that will be x to the 3rd power minus 2x squared. And now what we're going to do is take that 75, we're going to write it in general form. So we're going to equal this side to 0, and we will have x cubed minus 2x squared minus 75. Okay, so if we find the solutions, okay, I'm going to take a second. Okay, so I graphed the polynomial of 3rd degree that we have, and as you can see here, you could just see like a line. It almost looks like a vertical line, so you might be inclined to think it's not even a function. But if I zoom out, you could see, oh, it kind of gets distorted weirdly. But anyways, if we go back to this, we could see how it does cross the x-axis at 5. And so that's what I called an educated guess. And so if I was to test to see if that is in fact a 0, remember I get the coefficient, so 1 for x cubed, negative 2 for x squared, and we don't have an x, so I must put a 0 as a placeholder, and then my constant term is of 75 negative. So by checking that, I will get, let's see, 5 times 3 is 15, and then 5 times 15, 50, 25, yep, 75. So yeah, that is in fact a 0. So we have this in cubic, and then here this will be square, the new coefficients. So, oh, that's what they meant here. So right here from this polynomial, we it says here that the solutions that come from that polynomial, and I mean, you might have to use the quadratic formula, but you could also look at the graph and think there are no more x-intercepts happening, so then the other zeros must be imaginary. And so we don't need them to answer a question such as what is the side of the mold to make a pyramid, because you don't want imaginary numbers there or negative numbers. So from here, we consider our only solution to be 5. And so that is what we need for x. We need x equals 5. And so on this pyramid, the way that it will work is each side will be equal to 5. And then the height, which is 2 inches less, will be 5 minus 2, which is going to be 3. And if we were to calculate the volume of the pyramid that way, it will be 1/3 times the area of the base, which will be 5 squared, 25, and then times the height, which is 3. So 1/3 times 3 is a 1. 1 times 25. There we go. So what is the answer here? The side of the base is 5 inches and the height is 3 inches. And that is the last period. Sorry this video is so long, but so many things to cover.